Hello class! Today we are going to talk about Euclidean geometry versus spherical geometry. Now if you remember a few videos back we talked about this. We said that geometry was an axiomatic system, which means that it follows the rules. But the thing is, all of these rules are based on assumptions, some basic assumptions that everything else follows along. If this is true, then that means all of this other stuff is going to be true. And Euclidean geometry, this is what we learn, right? We talk about Euclidean geometry, and the most basic assumption here is that everything is built on a flat surface, which we call a plane. And we draw it with these little parallelograms like that, right? And because everything is on a flat surface, what this means is that lines are straight and they can go on forever, like this one here, right? Pretty basic stuff. And so one of the basic things we got here is that if you have a point that is not on the line, you can draw only one parallel line through that point. All right? And so there we go, a parallel line through that point. If I turned this line any at all, so there would be a different line going through that point, well, then it would intersect somewhere over here, over there, eventually, right? And so you can only have one parallel line through a point that's not on the original line. Another thing that we get is the shortest distance between 2 points is a straight line. Y'all probably heard that before lots of times, right? If you want to get from point A to point B, you just walk in a straight line, and that's going to get you there in the shortest distance, right? And one of the other things we're going to talk about that's true in Euclidean geometry is that the sum of the angles of a triangle is 180 degrees. This is something everybody knows, okay? Doesn't matter what triangle it is, you take all the corners, you add them up, and it's 180 degrees, right? Not a big deal. But there is one small, little bitty, teeny tiny problem with Euclidean geometry. The world is not flat. We do not live on a flat surface. We live on a sphere. Well, close to a sphere, right? And so Euclidean geometry doesn't always work for things on the globe, which brings us to spherical geometry. In spherical geometry, we have a totally different base assumption. Instead of assuming that everything is built on a flat surface, which we call a plane, we, in spherical geometry, will assume that everything is built on the surface of a sphere, which they call a plane. All right? This is the spherical geometry's version of a plane. They say, well, it's not flat. A plane is the surface of a sphere. So that's different. And because that's different, you can't exactly have a line going straight forever, because if you do, notice the line doesn't stay on the sphere, does it? It touches the sphere at one point, but it's not going to stay on the sphere. So that definition of a line is no good. We need a new definition of a line. And so the definition that we've come up with for spherical geometry, a line is a circle on the sphere that has the same center as the sphere. And we call these great circles. So this green one right here goes around. Center of the circle is the same as the center of the sphere. These ones that are going up and down, these are lines on a sphere. They are the great circles. This one going right here, not a line, because it doesn't have the same center as the center of the sphere. Center of this little circle here is way up here. The center of the sphere is way down there. So this is not a line. That's actually called a segment. So that's kind of weird, right? Well, because that is true, if I have a point that is not on the line, I can't very well draw a parallel line through it. Okay, so for example, this little one going this way that looks parallel, well, it's not actually a line. It's a segment, because it doesn't have the same center as the center of the circle. It's not the center of the sphere. It's not a great circle. I could draw a great circle going around this way, but it's going to intersect my first circle, isn't it? In fact, there is no way I can draw a great circle through this point that will not intersect that first circle that I drew. In fact, not only that, every great circle will intersect every other great circle at least twice, which means there's no such thing as parallel lines in spherical geometry. All right? Another thing with spherical geometry is that the shortest distance between 2 points is not a straight line. All right? It's a great circle. because a straight line would cut through the inside of the sphere, right? And we can't do that. This is why, if you look at flight paths for planes, notice they're all curved. Every single one of these flight paths here is a great circle on the sphere of the Earth. All right, so let me move that out of the way again. So the last thing we talked about there was the triangles, right? So look at this triangle that I have drawn here. I drew it badly, but that's okay. Following this, I've got a 90-degree angle, a 90-degree angle, and a 50-degree angle. Notice that is more than 180 degrees, isn't it? In fact, on a sphere, in spherical geometry, the sum of the angles will always be more than 180 degrees. Every single time. It'll look like this. You could widen this up and you could have 90, 90, and 90. You could have 3 right angles. You could have 2 right angles and an obtuse angle if you wanted to. And that would work on a sphere. That does not work in Euclidean geometry where everything is flat. So that begs the question, if we live on a sphere, why do we use Euclidean geometry? And here's the thing. Yes, we live on a sphere, but that sphere is really, really big, right? And so from where we are locally, you walk outside, everything looks flat, right? It looks like you're on a flat surface, and so Euclidean geometry works in local stuff. Just working on a piece of paper, it's fine. Even within a city or a state, everything is flat, it's all good. But globally, if you're looking at a global scale, you need spherical geometry. Because on a global scale, then the curvature of the Earth actually is big enough to matter. All right? So when looking at big stuff like intercontinental travel, we use great circles, we use spherical geometry. But local travel, things like that, Euclidean geometry is good enough. So again, the basic differences: in spherical geometry, everything is on a sphere, whereas in Euclidean geometry, it's on a flat surface. Right? Lines, we know what lines are. They go on forever and they're straight. In Euclidean geometry, spherical geometry, they are great circles. They have the same center as the center of the sphere. And because of that, there are no parallel lines in spherical geometry. The shortest distance between 2 points in Euclidean geometry is a straight line, but on spherical geometry, it's a great circle, like those flight paths for airplanes. And the sum of a triangle on a sphere will always be more than 180, but if we're talking Euclidean geometry, what we're used to, it's always going to be 180. So we're still going to be dealing with 180. We're still going to be dealing with Euclidean geometry where everything's normal and flat the way that we like it because it's easier. But you did need to know about spherical geometry. Know that there's other stuff. We are not going to talk about hyperbolic geometry, which is really weird, or some of the other curved geometries that can be absolutely nuts. So, anyways, there it is, Euclidean versus spherical geometry. Hope you found that useful. I will see you in the next video.